Hey, good morning, everybody. Thank you for being here. My name is Reimi Konagaya. I am a second-year PhD student from Waseda University, Tokyo, and I've come to ASSISI with two of my research group members, Professor Ken Naito. He is my supervisor and also the corresponding author of this paper, and also Mr. Kobayashi. He is also a graduate student, a master's student, and he will be talking after me. And after Mr. Kobayashi, I will be giving another talk about my research, a different aspect about my research. So my first talk right now is titled Development of Weak Cold Fusion Engine, Fusine, assisted by molecular chemical reaction, based on double focusing compression over 1000 bar and 7000 Kelvin due to pulsed supermulti-jets colliding. Okay, so previously we proposed a new principle for generating reactions, which is called focusing compression due to pulsed supermulti-jets colliding. In this principle, pulsed multiple high-speed gas jets are injected from the sidewalls of the chamber, colliding around a singular point at the center of the reaction chamber, causing fast chemical reaction and weak nuclear reactions. This new combustion principle will achieve high compression ratio around the collision point, leading to fast reactions, high power, and high efficiency, while maintaining relatively silent combustion due to reactions at the chamber center far from the solid wall. And also, there will be no heat loss at the chamber wall due to encasing of the reacted gas around the chamber center and increasing heat resistance. So first, in a shock tube generating supermulti-jets having shock waves at the front only once, the flow field near the collision point of supermulti-jets is visualized. And first, I will show results for 14 jets colliding at an inclined angle. And at an inclined angle, I mean that the passes for the supermulti-jets connect to the center of the chamber, the reaction chamber, at an angle of 45 degrees. So first, this flows the flow field of air. We can see the position of the shock front, which is here, and the size of the upstream mushroom vortex, which can be seen here. An emphasis is placed on the fact that experimental flows show axial symmetry after the supermulti-jets collide on the center axis, which may indicate stable compression due to collision of the jets. So next, in a shock tube generating supermulti-jets having shock wave at the front only once, pressure increase at the collision point of supermulti-jets is measured. And this time, we will measure the pressure increase for the collision point of 14 jets colliding on a same plane. And by same plane, I mean the jets collide at an angle of 90 degrees against the axis of the chamber, the reaction chamber. So this shows the experiment result of the pressure increase which was obtained near the collision point of 14 jets colliding on a plane surface. The maximum pressure was over 700 kilopascal, which is approximately 18 times that of the initial chamber pressure. High pressure increase than the intake was seen for experiment. And I'd also like to point out that experiment result was repeatedly or reliably obtained, with the maximum pressure value varying within less than 3%. So to summarize up to this point, pressure around the collision point of 14 pulse jets placed on a plane in a weak cold fusion engine developed originally by us is first measured by varying the pressure transducer position without chemical and nuclear reactions. High pressure ratio over 18:1 is reliably and stably occurred with variation of about 3% for peak pressure, while variation of intake pressure is less than 1%. Cases with strong disturbance also indicate stable and high compression, which I will show results at the end of my presentation. So next, I'd also like to explain about the mechanism of the axial symmetry of the collision of supermulti-jets. So in this diagram, when the center jet of the three jets in this example is slightly inclined to an upper angle, the upper part around the collision point becomes a relatively higher pressure, which will result in a force towards the low pressure area, resulting in the center jet to return to a horizontal angle. So next I'll show the prototype reaction chamber or engine we used for combustion experiment. First, 14 supermulti-jets enter through the intake. Then, pulse jets are generated by a rotary valve. This is the rotary plate valve, which is installed in the middle. After that, fuel is injected from the injectors between the rotary plate valve and the collision point of jets. Finally, 14 pulse jets collide at one point in the center of the reaction chamber and combustion occurs. The engine mount can move freely to the right and left on the rail. And a load sensor is fixed between the engine mount and the rail, which measures the thrust value when combustion occurs. So this table shows the engine specifications and main conditions of the combustion experiments we have done. The reaction chamber diameter is very small, only 18 millimeters wide. The number of nozzles for supermulti-jets is 14, and the fuel we use for the 14 injectors is regular gasoline. The oxygen concentration in the air supply is very low, about half. And the inlet pressure just before intake of the engine is low, only 0.3 megapascals high. So this photograph shows the result of the combustion experiment, which is taken around the reaction chamber exit. You can see the strong light due to combustion occurrence, which can be observed. And next, I'll show a movie of the combustion experiment. Okay, so that was a repetition of the combustion experiment result we have done. And as you can see from the movie, it shows that the test bench, which weighs nearly 500 kilograms, is moved to the left, although the upstream tank pressure is very low, only 0.29 megapascals high. And also the reaction chamber diameter is very small, as I said, only 18 millimeters wide. Okay, so next I'll show some time-dependent photographs of the combustion occurrence. We started doing combustion experiments about 3 years ago, and over the course of 3 years, we've obtained results for the combustion experiment about 30 to 40 times, and these show results of some of the experiment results we have done. So in each combustion experiment, you can see that we've obtained combustion several times, and we have, for each case, we've obtained the strong light due to combustion. So as I've said, fuel is only injected for a very short period. And next, I'll show a very important result for this engine. In a combustion experiment done with our engine, we can see the pressure increase, which implies combustion occurrence. This figure shows the wall pressure and the wall temperature obtained at the reaction chamber wall. As you can see, when the wall pressure is high due to combustion, the wall temperature is nearly at an atmospheric level, which shows nearly complete air insulation, which will lead to high thermal efficiency. And I'd also like to point out that this nearly complete air insulation effect hasn't been achieved by engine researchers for over 100 years. So next I'll show some results of the thrust that we obtained from our combustion experiments. Thrust of about 103 to 167 Newton is obtained for several cycles at startup of this engine. For auto ignitions of gasoline, although upstream tank pressure is only 0.29 megapascal, and reaction chamber diameter is very small, only 18 millimeters wide. Nearly the same value of thrust is obtained by calculation from the wall pressure that we measured, based on the pressure near the collision point, which was measured by experiment. I'd also like to point out that these values are relatively high compared to rocket engines of the same small size. So to summarize up to this point, fast chemical reaction of hydrocarbon fuel and oxygen in the reaction chamber engine using single focusing collision of 14 jets is reliably obtained, which indicates high power at level of twice or more of very small traditional combustion engines having a reactor chamber diameter of about 20 millimeters wide for air-breathing vehicles and rockets at the intake pressure of about 3 bar. So next I'll show some conversion analysis. Let us measure the specific thrust of this prototype engine to compare with the LE5 engine for the Japanese H-2A rocket. The converted specific thrust is 353 to 453 seconds for a new engine. This implies a possibility being equivalent to that of LE5. And about this conversion analysis, I'd like to point out an important point that we've considered, which is what happens when we increase the jets to 26 and place them in a spherical pattern, like this. And this is a computation result, which I will show more results in the second presentation. We can see that the pressure at the collision point increased to over 70 megapascal, which is over 2,000 times that of the initial chamber pressure. And also the temperature at the collision point was nearly 2,000 Kelvin. So you can see that very high level of pressure and temperature increase, which is more than enough to induce autoignition, is possible with this principle. So to summarize up to this point and to the next point of my research, experiments shown above and theoretical considerations clarify that chamber center collision of double pulse supermulti-jets of high-speed gases without nuclear reactions brings potential of high compression over 7,000 Kelvin. This double pulse collision and the value of 7,000 Kelvin I will explain more in my second presentation. When the number of jets is increased to 26 placed spherically and the double pulse collision of the jets, 2 collisions during a short interval is done. The next engine, modified by using the double pulse collision of jets, is repeatedly operated so that the second stage of focusing collision of pulsed supermulti-jets of palladium-hydrogen or palladium-deuterium encloses hot vapor water at a level of 3,000 Kelvin, which will lead to much higher temperature, which may bring weak fusion and higher power. Even collision of single pulse jets leading to 1,000 Kelvin may be enough for achieving weak cold fusion. So next, we here show experimental results of the durability tests of a concrete injection system of nanoparticles such as palladium and H2O, which is designed by us, a key point for realizing weak cold fusion. These pictures shows the injector system for supplying nanoparticles such as palladium and H2O at a point far from the reaction chamber. We here employ only conventional gasoline fuel injectors for automobiles. And this shows the result of the durability test of the injector we used. The injection rate is almost stable. For over 1,500 minutes, we have done for mixture of H2O and nanoparticles. Injection is not clogged. And also 1,500 minutes imply driving of a car for over about 2,000 kilometers, in case that only chemical reaction occurs. Therefore, if weak cold fusion occurs, we can say that longer drive is possible. Moreover, we will release the outline of this new weak fusion engine, Fusine, to the public because we must find a place in the world where this developed prototype engine can be safely tested. This is actually my first time presenting at an ICCF conference, but my supervisor, which is the director of this research, Professor Ken Naito, has given a talk at the ICCF in Sendai and the one in Korea, so some of you may remember the talk about our engine. He has worked in the engine research of Nissan Motor Company. Therefore, my supervisor, Mr. Ken Naito, and Tomotaka Kobayashi, our graduate student, and I wish to hold further discussions with anyone interested in this engine. So these are conclusions and outlook of my research. Our first prototype engine developed, which is weak cold fusion engine, Fusine, assisted by molecular chemical reaction based on double focusing compression due to pulse supermulti-jets colliding. In principle, fundamental experiments on molecular chemical reaction reliably and stably show potential of very high power and thermal efficiency, while having nearly complete air insulation and being relatively silent. The injection system for stable supply of solid particles, such as nanopalladium, is proposed, which has durability. We will soon start basic tests of weak cold fusion in another constant chamber. So during the next year, we will modify the present prototype engine, in which the number of jets is increased to 26. Also, we must find a place where the weak but strong cold fusion experiment test of the present engine is done. And because I have a little time left, I'd also like to supplement on the stability of the collision of supermulti-jets. So these are experimental photographs we took after the collision of the jets, and they show the flow field when disturbance is added to inflow of the compression device. These pictures shows the flow field after the collision of 8 supermulti-jets. And in these 4 pictures, a disturbance was added, and a half of one of the jets, the entrance of jets, were clogged. And this shows a disturbance we added in which one of the entrance of the side passages were shut. So as you can see, not much of the axial symmetry is broken, even if we add the disturbance to the inflow of the jets. These next experiment results show the pressure increase near the collision point when disturbance is added to the inflow of the compression device. At the upstream point of the inflow of the compression device, we introduced a metal obstacle. We fixed a metal obstacle, so we added disturbance to the inflow of the jets, which come from this direction. This shows results when no disturbance was added, and this shows results when this obstacle was added, which amounts to about 7% disturbance to upstream flow of the compression device. So as you can see, although the variation is slightly larger, the maximum pressure increased to nearly the same value as without disturbance. So we can see that this principle is strong against disturbance. Not much of the axial symmetry and the pressure increase, it doesn't change much when disturbance is added. I'd also like to say about 5 physical reasons why the collision of supermulti-jets is stable. The first reason I explained in my presentation, about how the phenomena, it may be stable by nature. And the second point is point compression at reaction chamber center is mainly produced by collision of very thin spherical shock fronts generated stably and repeatedly, which leads to stable pressure increase at the chamber center. The third reason is that the jets coming after the shock front are in laminar flow, because early stage for pulsed flow shows potential flow, as is well known from fluid dynamics textbooks. And the fourth reason is that collision point of jets in laminar flow region upstream from turbulence. The figure on the right-hand side indicates that there is a certain laminar jet length over 2.0, a region where the jet is straight, which is a characteristic of jets that is shown in several textbooks. On the other hand, the smallest R/D ratio for nozzle diameter of the supermulti-jets we used in this prototype engine is about 1.35. Thus, the conditions similar to nearly laminar straight jet will also lead to stable collision of the supermulti-jets. And the fifth and final reason for the stability of the collision of supermulti-jets is there's less shear stress between the jets, because there's very little stagnant region between the neighboring jets. This fact will lead to nearly laminar flow, whereas the computation of a single high-speed jet injected into ambient air, which is shown in this picture, done by the present numerical method, we also did numerical computations on the CIP and CUP method are validated by agreement with various experimental data, has a relatively strong shear stress around the contact surface between the jet and the ambient air, which results in turbulence. I will show some more computation results in the next presentation, in which I will show that the computation agrees very well with the experiment that I showed in this presentation. So with that, I finished my presentation. Thank you very much for your attention.
Why do you say that the weak fusion reaction? It's a fast, and then I guess you don't have any indication of a nuclear reaction is really occurring. Is that right? And
Okay.
then what kind of a nuclear reaction are you expecting from your experiment?
Okay, I was planning to discuss further about that in my next presentation. So yeah, in my next presentation, I will show some ideas about how we will use this principle to generate.
Why you are saying that weak fusion?
Okay, my professor would like to talk about that.
What weak? And, we show the strong chemical reaction, but weak, we hope the roughly say the 2 times of the energy in comparison with the chemical reaction. That is weak, I said. That is a minimum point for application in my mind. So yesterday there are some people that talk on the figure that energy per hour plotted against temperature. Now less than 2,000 Kelvin. But I calculated, I roughly calculated from the figures that if 7,000 Kelvins, the 2 times of the power will be obtained. That's a rough comment. Okay?
It's not. Come on. I have 3 questions concerning your presentation. The first, stability is not clear because of jet stability, interaction of jet stability, shock wave stability. It's different mechanism. It's the first. The second, it's stimulated combustion chemical reactions. But I agree with that cold fusion is very far from the chemical reaction. And concerning the chemical reactions, what's the analysis of the final products of your combustion?
I roughly understand it.
Completeness of your combustion. What is the completeness? I hope very bad completeness and many of the soot particles inside of your reactors. It's bad situation for the cold fusion.
Yeah, for first question, instability, the collision. But we have more data. One is computation result, but if the collision is not simultaneously, in that case, much more higher pressure we get. Yeah, some evidence we have, and also we showed the 5 reasons, but 6 is one more reason exists, and yeah, but of course, when we start this engine development, we check the stability of the collision, focusing collision, but stable. And many evidence we have. And we showed the 5 reasons, experiment and the computations. The second is, what is the double pulse focusing? Here, どこだっけ? First どこだったっけ? 最初に水ができる。これ、here the second stage of focusing collision of pulsed supermulti-jet encloses hot vapor water at the level of 3,000 Kelvin generated by combustion from the first collision of jet of hydrogen and oxygen. In this experiment, we showed the fossil fuel, but for this case, we will use hydrogen oxygen combustion at first. The hot, very hot water vapor assists lead to the very high temperature region. After that, the second collision of the supermulti-jet lead much more high temperature region. Okay?